that Professor Ken Ono will have a talk on variants of Rayman's conjecture. So could you please start?
Oh, okay. That's very, very fast. Okay, I can, please. So I'd like to thank the organizers, Professors Tsuchioka, Hikami, and Kato for kindly organizing this workshop. And despite the pandemic, it's wonderful that we can still meet electronically. And although this isn't perfect, I would like to see everyone in person. So maybe next year I can come to Japan and see everyone in person. But in the meantime, it's still wonderful to have an opportunity to see human beings, right? We're in quarantine here in the United States, so I hardly ever see anyone outside of my family. And so what better way to see people than to talk about some mathematics? So thank you very much, and let me get started. So this lecture is called Variants of Lamer's Conjecture, and this is joint work with Jennifer Balakrishnan, who is at Boston University, one of my PhD students, Will Craig, and a University of Virginia postdoc by the name of Wei Lun Tsai. He just finished his PhD, and he's a postdoc with us here now in Virginia. So this will be a very expository talk, so let me begin very slowly. There's no better way for me to start to talk about these theorems than to remind you of the great Indian mathematician Srinivasa Ramanujan. Ramanujan left behind notebooks that people still study. He wrote around 30 papers that which cover various areas of number theory. But even among all of the contributions that Ramanujan made to mathematics, I think one paper stands out as being particularly important, and it's a very modest titled paper called On Certain Arithmetical Functions. My guess is that most of you know this paper. If you don't know it by name, you certainly know about the consequences of this very important paper. This very important paper really isn't about many arithmetical functions, basically related to the coefficients of a very select group of distinguished modular forms, of which perhaps the most important is the delta function. Ramanujan in this paper defined his famous tau function, denoted here in red. It can be described many ways, and maybe the most convenient way to describe the numbers tau of n is that they are the coefficients of the Q series you get by raising out this infinite product to the infinite problem, infinite product to the 24th power. So number theorists have for a very long time been interested in a sequence of integers that are the coefficients, 1, -24, 252, so on and so forth. And it turns out that many of the properties of this single sequence have given rise to some of the most important structures that we get to enjoy today in the theory of modular forms. But as a exposition, let me begin by highlighting some of the famous ways, certainly for students if you haven't seen this. So the delta function, which is this Fourier expansion in Q, where Q throughout is e to the 2 pi I z, is well known as a cusp form. It's the unique normalized weight 12 cusp form for the full modular group SL2Z. And one of the things that means is that as a function on the upper half of the complex plane, for every Möbius transformation, for every 2 by 2 matrix ABCD with integer entries in SL2Z, this function reflects back to itself in this way. So it's not exactly invariant under the Möbius transformations, but up to the 12th power of the denominator of the Möbius transformation, the function is fixed. This next remark, this box, is not an understatement. If you truly understand this function delta, then your ideas could be put to use in many different areas. So in arithmetic geometry, the properties of the delta function play an important role explicitly in the study of elliptic curves, and it plays an important role in computing invariance related to the Bertson-Swinnerton-Dyer conjecture. Not to mention that the modularity of elliptic curves involve modular forms of a very similar type. If you're interested in number theory, classical number theory, the stuff of partitions or quadratic forms, then the delta function is not new to you. It's also, of course, related to the recent works on Saphir packing. If you work in string theory or mathematical physics in mirror symmetry and the like, you've come across the delta function. And somewhat more recently, I guess, functions like the delta function and its relatives play an important role in representation theory. So those are just some very basic comments that I'd like to make about how important this function is. And now let me turn to some of the striking properties that the tau function satisfies that has been generalized to arbitrary Hecke eigenforms. So Ramanujan himself conjectured that this sequence of numbers tau are multiplicative. He didn't know how to prove them. After all, for him, these were the coefficients of a complicated infinite product. And it would be through the work of Mordell, who basically gave the genesis behind the ideas of the Hecke operators. Hecke would later develop this fully. Mordell proved that the tau values are multiplicative. So if n and m are relatively prime, then tau of nm equals tau of n times tau of m. Now, this is not a completely multiplicative function. And so to determine its complete multiplicative properties, you have to consider how the tau values are related in a sequence of prime powers. And there's a very beautiful theorem. And the very beautiful theorem, which is the second part of Ramanujan's conjectures here, is that tau of p to the m, for every m, is this two-term linear occurrence relation and tau evaluated at smaller powers. So I said it in a very precise way. So for every prime p, there is a two-term linear occurrence relation that pulls out and determines the values of tau on these prime powers. Of course, this theorem was later beautifully developed into the theory of Hecke operators by Hecke. And by the 70s, people like Atkin and Lehner, and then of course also people like Miyake in Japan and Winnie Lee here in the United States developed this further. And all of us get to now enjoy a very rigid, beautiful theory of Hecke operators acting on spaces of modular forms where there are beautiful maps between modular forms with respect to different kinds of groups. It's a very beautiful network. And so we are thankful to Ramanujan for making that conjecture. Another kind of result that Ramanujan found in this case and proved, he didn't prove his multiplicative conjectures, are some beautiful congruences. So if you're familiar with some of the work that I did early in my career, you know that I really am quite fascinated by congruences. And if you know my email address, some of Ramanujan's congruences have made their way into my email address. So Ramanujan proved some striking congruences between his tau coefficients and various incarnations of divisor functions. Perhaps the most famous is the one that relates tau of n to the sum of the 11th powers of the divisors of n mod 691. I put the 691 in red for a number of reasons. The 691 will appear later in some of our theorems, and it appears later because of the connection between Galois representations and Eisenstein series in what's called the residually reducible case. And those ideas will be very important to us. So Ramanujan proved these congruences by formal power series manipulations. He was a master. He was like Don Zagier before there was Don Zagier. Or maybe we should say Don Zagier is the late 20th and 21st century version of Ramanujan. What's striking about these congruences is that Serre and later Deligne recognized that these congruences go far beyond the stuff of identities. They go far beyond the manipulation of power series. So Serre saw glimpses of a theory of L-adic Galois representations that, if one could show, correspond nicely to the theory of modular forms, would allow you to reformulate congruence properties in terms of algebraic number theory. So that is exactly what Serre conjectured and Deligne later constructed explicitly, and it's now a fact. Given a modular form like delta and any prime L, there is an L-adic Galois representation that interpolates not only the weight, that's the easy part, but literally interpolates all of the Fourier coefficients at primes for modular forms like delta. And if you were to chop off part of the L-adic representation, as I suggest here, if you just study it mod L, then you get the congruences rather beautifully. It becomes the stuff of algebraic number theory. Of course, perhaps the most important consequence of this realization is that Wiles made use of the modularity of elliptic curves. He proved that all elliptic curves are modular by relating their p-adic Galois representations to those associated to modular forms. And he found that there's a one-to-one correspondence between isogeny classes of elliptic curves over Q and the Galois representations associated to weight 2 Hecke eigenforms with integer coefficients. So these congruences, perhaps they may seem quite elementary at first glance, but it's certainly the case that the theoretical depth and consequences of these results are very important. Finally, the last thing I'd like to point out about Ramanujan in this paper is that he conjectured that for all primes p, that the absolute value of tau of p should never exceed 2 times p to the 11 halves. If you haven't been following the theory of modular forms, or if you happen to live in 1916, this little conjecture would be very easy to miss. It looks strange because why not be content with showing that the absolute value of tau of p is bounded by 2p to the 50th? Well, it turns out that Ramanujan's conjecture is correct. I think most of you know this is one of the concrete first examples of the importance of Deligne's proof of the last of the Weil conjectures. And what's striking about this is not only did Deligne prove Ramanujan's conjectures, he made it clear that this exponent of 11 halves is optimal. And this is a very long story that continues to live on to this day. People like Richard Taylor and others have been studying and have proven what's called the Sato-Tate conjecture, where one studies the distribution of tau of p in this admissible range from negative 2p to the 11 halves up to 2p to the 11 halves. And if you haven't seen those works, what those works illustrate is that this is the best possible bound. And once you have this best possible bound, people like Sato and Tate were later able to formulate this beautiful new kind of distribution called the distribution of Frobenius angles. And it's still a very hot topic today. Despite that, the conjecture of Ramanujan was amplified later by Peterson and now is amplified and generalized to many different settings, higher rank automorphic forms, and what's called trying to break convexity for values of L functions in the critical strip. So there's a whole mantra called the Ramanujan-Peterson conjectures. Peter Sarnak and his many followers are world experts on this. The Langlands program depends on this, and there's a large body of mathematics whose proofs are contingent on the truth of Ramanujan-Peterson. So in this first few minutes, I wanted to just start by saying the delta function is rather remarkable. This innocent sequence of coefficients have inspired inarguably, some of the deepest works that we now take advantage of in number theory. Great. So you may ask, in view of all of these wonderful theories developed by the deepest thinkers of our generation, how could it be that we don't know everything about the tau function? And this is the topic of today's talk. And a famous conjecture by Lamer is that for every positive integer n, tau of n is never 0. And despite everything we now know about modular forms using the ideas that have grown out of the results I described earlier, this problem has remained open. What do we know? So what I stated here for Lamer's conjecture is not precisely correct. What I mean in this theorem is, this theorem is not stated correctly. What I really mean is if tau of n is ever equal to 0, then there is a prime n for which tau of n is 0, right? By multiplicativity, if tau of n is 0, then tau of nm is 0 if m is co-prime to n. My point here is that Lamer himself proved that if tau of n ever vanishes, there is a seed prime that dictates that vanishing. And so if you could prove that tau of p is never prime, is never zero for any prime, you will have then proven Lamar's conjecture. And very little work was done on that for over 30 years after Lamer proved his theorem, which actually isn't difficult. And Serre, making use of his Galois representations and the Chebotarev density theorem in a very nice way, he was the first to prove that if tau of p ever vanished for a prime p, the set of primes p for which tau of p vanishes has density 0. And there are probably maybe 10 to 20 papers following up on Serre's famous 1981 work. And in analytic number theory, people have worked on it. And I think this is currently the world record. The number of primes up to x for which tau of p could vanish is less than this log x squared over log x. What is pi of x? Pi of x is the number of primes up to x. So this ratio in red is an upper bound of the proportion that could be a counterexample to Lamar's conjecture. And so of course, as x goes to infinity, this goes to 0. And this is our, I think, still the best result along the lines of Lamar's conjecture. So people have computed, and I'm not sure it's worthwhile to keep computing. So if you're wondering, at least as of 2013, tau of n is known to be non-zero for n up to this large number. Okay, I'm not an expert on any of these calculations. The first few calculations were theoretically derived using the Chinese remainder theorem and congruences. And these, I'm not exactly sure how those calculations were done. So I regret to say that Lamar's conjecture remains open. But please don't go away, because it turns out that there is a question that I want to answer. And before I address that, I want to highlight a recent result in the spirit of the direction I'm going in that was recently proven by Frank Caligari at Chicago, and I think his former student Sardari. So if you fix a prime p, let's say 17, and a level, so say level 1 or level 15, just a level of a congruent subgroup. But the point is, fix a prime p, say 19. They prove this beautiful theorem. It says that at most finitely many non-complex multiplication new forms f will have that coefficient 0 at that prime p. So imagine we were in the Atkin-Lehner world and we were able to walk among the new forms on some group, let the level aspect move. Let the weight aspect move. If we only studied the Heck operator TP, the one Heck operator, pardon me, say T19, then there will most be finitely many non-CM forms for which the P coefficient vanishes. So this is proven much in the spirit of the Serre theorem, except we now let the weights go to infinity, and we have enough control that if the weight is sufficiently large, then the P coefficient can't vanish. This is impossible to make effective, but in terms of an explicit theorem, I think this is quite nice. What I am interested in is, what is the truth if you give me a new form like delta? What can I say about delta itself? So the natural variation that you could ask is, well, can tau of n equal a given integer alpha? Lamer is interested in 0 for the obvious reason that multiplicative functions will vanish whenever it has the value 0. But as a number theorist, let's just ask, what integers are allowed to be the coefficients of delta? And the main point of my lecture is that we have devised a set of techniques that should allow you to answer this question for almost every odd integer alpha. And in particular, in forthcoming work, if everything works out, it can be extended to every non-zero integer alpha. So the spirit of this lecture is, it's step 1 in our little program to attack this question. And it turns out there's a lot that we can say. The only case where we are unable to say something good is unfortunately the case of tau of n identically being 0. We have ideas for every non-zero integer. So the starting point for this is this famous theorem from the late 1980s by the Murty brothers and Shori. And for odd integers alpha, they proved there are most finitely many n for which tau of n equals alpha. So I make the word alpha, I make the word odd red because everything else in this talk will be about odd integers alpha. But like I said, part 2 of our program would be dealing with even alphas that happen to be non-zero. So many of you will probably be thinking about how we could relax the condition in odd. We've already done some of that. And if time permits, maybe I'll comment on what you have to do in that direction. So this is a great theorem. It says that for an odd number like 15, tau of n equals 15 for a most finitely many n. Now, this paper, the proof is very short. The reason it's very short is that the proof depends on very deep work of Alan Baker on linear forms and logarithms. And if you've never studied theorems on linear forms and logarithms, you'll discover that there's a large body of Diophantine type problems that one can show have at most finitely many integer solutions, except those solutions could live in a range with size up to e to the some constant, where that constant isn't really effectively computable or is quite difficult to compute. So that is exactly the situation here. No one has been able to prove using that method that tau of n couldn't be 5. So along these lines, before the ideas I'm going to talk about, the only effective results that I'm aware of, I'm pretty sure this is the only thing that anyone has ever published, is that alpha equaling plus or minus 1 in the work of Ligeros and Rosier are the only situations that people were able to make effective in Murty, and Shorey. So the task really is, given an odd integer alpha, can we show that tau of n is never alpha? Or if tau of n ever equals alpha, can we compute those n for which tau of n is alpha? And what I want to tell you right now in a sentence is we know how to do that. So the main takeaway from this lecture is that in theory, and I will show you in practice explicit examples, in theory, determining whether tau of n equals an odd number alpha can now be done. So.
Okay, I found this on the web for in theory determining whether Calvin equals a number alpha can now be done.
Do you guys know who Siri is? My iPad here thinks I was talking to her. So she answered a question. So I apologize for that. So our results depend on theorems like this on this slide. So for the purposes of speeding along the exposition, I'm going to now focus only on the situation where tau of n is a power of an odd prime. So L will be an odd prime. And as I describe this, you'll discover it's not so difficult to generalize. So here is the first theorem, and it might be surprising to you. Let's look at it. If L is an odd prime, that's fixed. If tau of n in absolute value ever equals L to the m, then this theorem essentially locates or greatly restricts what n is allowed to be. If tau of n in absolute value is ever a power of an odd prime, then the n is itself must be a prime power. For tau to be a prime power, the n must be a prime power. But it's better than that. Not only is it the case that n has to be a prime power, the exponent d minus 1 in that prime power must have that d is itself prime. And not only must that d itself be prime, it must be an odd prime. And not only must it be an odd prime, it must divide the number L times L squared minus 1. And what I want you to notice in this theorem is that the conclusion depends on m in no way. The conclusion of the theorem doesn't use m at all. M is nowhere here. So suppose you wanted to show that tau of n equals 5, some positive power of 5. 5 to the 3rd, 5 to the 19th, any power of 5. So if L is 5, 5 times 24 is only divisible by which odd primes? 3 and 5. If L is 5, the only candidates for D are 3 and 5. So the way my theorem works is if tau of n is ever in absolute value up to sign a power of 5, then n must be of the form p squared, that's when d is 3, or p to the 4th. There cannot be a tau of p to the 8th that equals a power of 5. It would have to be tau of p squared for some prime p, or it would have to be tau of p to the 4th for some prime p. So this suggests an algorithm for solving tau of n equals a power of a prime up to sign. You first list the finitely many odd primes d that divide L times L squared minus 1, like I just did for you verbally. If L is 5, there's only two choices, namely 3 and 5. And then for each of those finitely many d, I have to solve for the prime number p this equation. And I have to convince you that we have, at least theoretically, the ability to answer this equation. And the point is, this is a Diophantine equation, and that's what I have to explain. So I will explain that in more detail, but I think you see why this is a very useful result. It greatly restricts where a tau value could be a prime power. The power doesn't matter. And if you carry these sorts of ideas out in full generality and use the computer, there have now been some papers. If n is bigger than 1, we've been able to show that tau of n isn't plus or minus 691. Plus or minus 1 was known before, as I mentioned. And if L is any prime between 3 and 100, tau of n is never plus or minus those L's. And if you're willing to work harder with a computer and use these ideas, these sets will grow. So, like I said, these results can be extended to tau of n being any odd. And if time permits, I might explain how you can replace odd with any non-zero integer alpha. So all of our theorems are actually quite general in the sense that for this talk, I don't need to restrict to just the delta function. I just need to restrict to a type of modular form. Let's assume that it has integer coefficients, one that has a residually reducible mod 2 Galois representation. If you don't know what that means, let me just tell you this is an easy thing to check. A modular form will have a residually reducible mod 2 Galois representation provided that all of its odd coefficients are supported at square exponents. This is something that is clearly true for the delta function. And if you are familiar with the modularity of elliptic curves, this condition holds for every elliptic curve that has a rational 2 torsion point. And actually, even every modular form with these infinitely many choices of levels, a power of 2 times m, where m is in this set. This is in a paper I wrote with Yuichiro Taguchi many years ago. Every modular form with these levels will automatically satisfy this residually reducible mod 2 Galois representation condition. So there's many of them. So the theorem I described before about locating coefficients that are powers of odd primes is exactly the same. The only thing that you require is that the weight be even and at least 4, and that the second coefficient be even. So if you know tau of 2 is negative 24, that's even, and that's why I'm able to use this theorem. So every one of those new forms on this slide has the property that this theorem will locate coefficients that are odd prime powers. Just to give you an indication of how easy it is to now write down infinitely many numbers that are just never Fourier coefficients, suppose the weight of your form, 2k minus 1, suppose it's divisible by 1 of 3 or 5, at least 1 of 3 and 5. So for example, if your weight is 16, that works. 5 divides 15. And the weight is at least 12. Then your form, provided it satisfies my Galois representation condition, has the property that the coefficients are never plus or minus 1 after the first coefficient. And you never get plus or minus an odd prime between 3 up to but not including 37. But you also do get that negative 37 cannot be a coefficient. So you may wonder, how come I didn't have plus or minus 37 here? Why did I separate this? Is it because my computer didn't run long enough to rule out plus 37? No, it's because our theorem is strong enough. Our theorem is strong enough to actually locate the coefficients that do occur. So if you assume the generalized Riemann hypothesis, I can make this list longer. It can go up to 97, but I can't get 37 back. And let me tell you why I can't get 37 back. I can't get 37 back because it's genuinely the ninth coefficient of a modular form of weight 16. It actually occurs. So I got a little bit ahead of myself. You may be wondering, do these theorems apply for weight 2 modular forms? They don't, and I'll explain in a moment why that's the case. Our theorem does a little bit better than restricting the location of coefficients that are prime powers. It actually locates them in situations we cannot rule out a coefficient. So if the weight is 4, and if the weight is 4, it turns out that the coefficients are allowed to be -11 or 37 and 19, right? It's allowed to happen. So in this theorem, so when the weight is 4, all right, so this is a little bit misleading because here I'm using the weight is at least 12, but you'll notice that I couldn't get 37 when the weight is at least 12, and that will also survive at 4. I can't rule out 37 as a coefficient when the weight 2k isn't as big as 12. So the analogous theorem when the weight is 4 leaves open the possibility that these numbers are all Fourier coefficients. But our method is so strong that it says that the only time that 37 could ever be a coefficient would be the 9th coefficient. So if you were to find a modular form of weight 4 and you want to know if 37 ever occurs, our theorem tells you check A of 9. If A of 9 is not 37, you never have to check again. 37 will not arise. Okay. And in the special case of weight 16, you can run your computer. You can find that 37 indeed occurs as a 9th coefficient of some weight 16 form out there. I forgot. Go to the modular forms database and you will find it. Great. So if you apply this in an example, the weight 16 Hecke eigenform E4 times delta, the famous Eisenstein series E4 times delta, it has no coefficients with absolute value and odd prime L between 3 and 37, and assuming GRH, you can go higher. Great. Now, although the theorem I really want to focus on is what I just described, and I want to explain how that works, I do want to indicate that our methods can be effective if you want to study theorems of the type that Caligari and Sardari proved. So suppose that alpha is an odd number, integer. Can it be the Fourier coefficient of a large weight form, right? So is there a weight that's so large that alpha cannot be one of these coefficients, again, assuming the Galois representation condition? And the answer is yes. So pick any L, odd, pick any prime L. And then for every prime power of that L, L to the M, for every prime power, we can prove that there's a constant depending on the sign, plus or minus, depending separately on L and M, that says that if the weight is bigger than that constant, then the nth coefficient is never plus or minus L to the M. What is important about this is that this constant is big O of L to the M. What does that mean? That means if L is fixed, this is linear in M. If L is fixed, the weight growing linearly in M is fast enough to rule out L to the M as Fourier coefficients. So it's a very tight window. So for example, if you want to study whether 3 to the M can be a Fourier coefficient, so L to the M, 3 to the M. If you want to know if 3 to the M could be a coefficient in absolute value, the answer is no for any form whose weight is bigger than this function in M. So I apologize about the 10 to the 32. That might as well be infinity, but for my eyes, that's not close to infinity. So this is bounded linearly in M. And this kind of phenomenon is true for every L. So the point is that the constant 2 and 10 to the 32, they depend on the choice of sign and L. But there's always a calculation like this that you can do. Lamer actually proved that there are prime values of tau of n. So when you look at our theorems, and I said that there are no odd primes that tau of n could be up to 100, it's not that there's a conjecture that says tau of n is never prime. That's not true. So in particular, Lamer himself computed tau of 251 squared. It's this gigantic number, and it is prime. And almost assuredly, there are infinitely many prime absolute value coefficients of delta. I can't prove that, but there are many reasons, heuristics that are compatible with what I'm describing here that suggest there should be infinitely many prime coefficients. But on the other hand, what I want to stress is you might think this is strange that tau of 251 squared is where the prime occurs. Well, it is impossible for tau of p to ever be prime. The Galois representation will demand that. So if tau is ever prime, it would have to be prime at an even power. It would have to be prime at a perfect square. And so in view of that, you might want to know how many prime divisors a coefficient tau of n should have, including multiplicity. So as usual, I'd like capital omega of n to be the number of prime divisors of n, including multiplicity. And I'd like little omega of n to be the number of distinct prime divisors of n. So before we prove this theorem, I would have always thought that the only comparison that you could get, the only lower bound or formula you could get or inequality you could get for the number of prime divisors of tau of n would be the number of distinct prime divisors of n by multiplicativity. I would have sworn that that would be the only way to get a lower bound on the number of prime divisors of tau of n. But that's not true. This theorem is a better lower bound. So the total number of prime divisors of tau of n is certainly at least as large as the number of distinct prime divisors of n, because we know that tau of a prime power is never plus or minus 1. That's that was the theorem of Liggeros and his co-author. But we proved something a little bit better, which is generally better whenever n is not a perfect square. So consider the factorization of little n, and for every prime that divides n, calculate the power of p dividing n, add 1 to it, and count the number of divisors of that number, one more than the p-adic valuation of n. Count the number of that divisors. Then take away 1 and sum over those primes. That's obviously always at least as large as the number of distinct prime divisors, but often it is much larger. Lamer's prime example is sharp. There's only one prime dividing 251 squared. It divides it to the second power. So our lower bound is this, which allows for this to be prime. All right, and an almost identical statement holds for all of the new forms with my mod 2 Galois representation hypothesis. Great. So I threw out there a number of results. The first result is showing that we can greatly restrict where prime coefficients could be or odd coefficients could be. And let me give you an outline of the idea. So here, let's just, for argument's sake, only study the case where tau of n in absolute value is a prime itself instead of a prime power. And I'll explain later where you relax to get the prime powers. So either you use the Galois representations or you just use an elementary identity of Jacobi that says that tau, the coefficients of the 24th power of the Dedekind eta function, mod 2 is determined by the third power of this change of variable applied to the Jacobi identity. And thanks to the Jacobi identity, the Q series that has tau as its coefficients, mod 2 is nothing but the generating function for the odd squares. Now that's very nice because if tau of n were ever an odd prime, that's a huge head start. N itself would have to be an odd square. So therefore, by Hecke multiplicativity, we now know that if tau of n ever equals a prime L, then n itself must be an even power of a prime. Again, that's using the fact that tau of n equaling plus or minus 1 only happens when n is itself 1. Therefore, if tau of n is going to be if tau of even prime power is going to be my number L in absolute value, what I'm really focusing on are these two-term linear recurrence relations in the power m. So if tau of p to the anything is ever going to equal to L, I want to study this sequence generated by these numbers. So the two-term recurrence relation depends on tau of p and p to the 11th, and the rest is just generated. So just an exercise. For every tau of p, this sequence is periodic mod L. Of course, it's a two-term linear recurrence relation. And it's not very difficult, elementary exercise, to prove that the first time the prime L divides any one of these terms, so the first time L divides a tau value, so let's call it tau of p to the d minus 1, you can prove d has to be a divisor of L times L squared minus 1. So I don't really want to go into much detail about that, but if you've ever played with linear recurrence relations, this won't come as a surprise. And if you've never played with linear recurrence relations, do so, and within half an hour, you'll find the proof yourself. So the first time L divides a term in this sequence, if it ever divides a term in this sequence, can be bounded. Now I'm going to make a very powerful claim. And my big claim, and you might not believe me, and I would not have believed me myself a year ago, but the big claim I'm going to make is that every term in this sequence, and now I am just truncating, I'm throwing out the 1. Every term in this sequence starting at tau of p. I'm going to make the very big claim that every term in this sequence is divisible by a prime that does not divide any previous term. So do you see what I mean? Tau of p squared will be divisible by a prime that tau of p didn't have as a factor. So walking along this sequence, I'm going to make the very big claim that every time you go up in a prime power, you'll get a prime factor that did not occur among any of the previous prime powers. If that is true, then for tau of p to the 2t to itself be a prime will require that the d I said a moment ago is itself prime, right? It will require that it is itself prime, because if it wasn't prime, then it would have to, well, I think it's pretty clear, right? And so that's great. So what that tells us is that if tau is ever a prime in absolute value, then d would have to divide L times L squared minus 1, and it also itself has to be prime. So then it turns out that this expression gives rise to an integer point on an algebraic curve over Z with positive genus. And by Siegel, all such curves have at most finitely many integer points. So this is my strategy. My strategy is, if this big claim is true, then if we could make Siegel's theorem effective, then we would be able to rule out integers as coefficients. So let me tell you how it works. So suppose you have an arbitrary integer sequence. We will say this integer sequence has a primitive prime divisor. A term in the sequence will have a primitive prime divisor L if the following are true. L divides the nth term, but L doesn't divide any of the previous terms. And if A of n does not have a primitive prime divisor, then we will call that term defective. If you've never studied this before, let me tell you about how I learned about this whole theory in the first place. I was reading some old classical number theory stuff from about 100 years ago, and I saw this theorem of Carmichael referred to. So this might be the first paper I've ever written where the Fibonacci numbers appear. And what Carmichael proved in 1913 is the Fibonacci sequence listed here that you all know have the property that the only defective terms are the numbers that I've turned into red. 8 is defective because it's only divisible by 2. 2 is itself a previous Fibonacci number. 144 is divisible only by the primes 2 and 3. They divide earlier Fibonacci numbers. But after 144, he proved every single Fibonacci number is divisible by a prime that does not appear as a factor of the earlier sequence. He does not give a formula for it, but he proves it exists. And when I learned that, I was amazed because I knew, and I think all of us who work on modular forms knows that Hecke's recurrence on prime powers is just a 2-term linear recurrence. So it turns out that some really smart people who I've actually known, and it's kind of embarrassing to me that I haven't known about their theorem. It was a beautiful theorem. I'm happy to tell you about it. Is quite general. It's about Lucas sequences. And if you don't know what that is, and I didn't really properly know this at all until quite recently. I knew some basic things, but not this beautiful theory. Lucas sequences are sequences that correspond to irreducible quadratic polynomials over Z. So suppose that alpha and beta are quadratic algebraic conjugates. So in other words, we suppose that alpha plus beta and alpha times beta are integers. Let's assume they're both non-zero and relatively prime. Let's also assume that alpha over beta is not a root of unity. Then the Lucas sequence given these two terms alpha and beta, just given by the numbers alpha to the n minus beta to the n divided by alpha minus beta. And these are the numbers that are generated by the 2-term linear recurrence relation given by the characteristic polynomial that has alpha and beta as roots. Now here is this amazing theorem that generalizes the phenomenon that Carmichael discovered for the Fibonacci numbers. I hope you're amazed by this theorem, and if you know this theorem, I hope you enjoy the fact that I'm still young enough at heart to find some elementary statements in number theory to be really beautiful and surprising. The kind of theorem that that gets you into the subject in the first place. So here's this theorem by Yuri Bilou, Guillaume Hanro, and Paul or Philippe Voutier. I don't remember his first name. And the theorem is that the Lucas numbers un of alpha beta for index n greater than 30 always have a primitive prime divisor. It's against the law for a Lucas sequence to not have primitive prime divisors after the 30th term. You can try, you can search, try to construct counterexamples, and you just can't do it. That's a beautiful theorem. The theorem is better than beautiful. Beautiful might not mean effective. This is beautiful and effective. So their paper, together with a follow-up work by Abu Zaid, who I believe was one of Yuri Bilou's PhD students, gives the complete classification. You can look it up. The complete classification of defective Lucas numbers is now known. If you write down a 2-term linear recurrence relation and you look it up in an atlas, if it doesn't appear there, then all of the terms are non-defective. This classification breaks into 2 parts. There are the sporadic sequences that are not geometric in origin. And then there are finitely many parameterized infinite families that come from algebraic geometry. If you're wondering, is 30 sharp? Yes. And I'll actually give you a sequence where the 30th term does not have a primitive prime divisor. So for our work, we will call a Lucas sequence potentially weight 2k modular at a prime p if the following are true. Let alpha times beta be p to the 2k minus 1. So this 2k will be the weight, and it's going to be like the determinant part of a Galois representation, or the last term in the Euler factor for an L function. And I'm going to define capital A to be the trace, or the negative trace. And I'm going to require that in absolute value, this trace satisfy the Deligne bound. Okay. And by brute force, using their beautiful theory, you can completely classify all the potentially modular defective Lucas sequences. Let me give you an example. I said that their classification breaks into 2 types, the sporadic and the algebraic geometric families. It turns out the sporadic is a very simple table. It's this. The only pairs A and B that have a defective Lucas number are listed here. What is B? B is P to the 2K minus 1. So the only prime powers, if you want to do tau of P or A of P, the only primes that ever come up are 2, 3, 5, 7, and 11. What are the weights? The weights are one more than the exponent. So one thing I want you to notice here, there are no such thing as sporadic, potentially modular sequences once the weight exceeds 4. For the weight 4, these are the only bad examples, and that would be for the Hecke operator T2, and that would be where the coefficient of A of 2 is either plus or minus 3 or plus or minus 5. Their theory is so explicit that I know exactly which numbers will then arise that are not divisible by a previous prime factor. I then said that the theory also has some counterexamples that lie in parameterized families. They arise in algebraic geometry, and they correspond to integer points of one of these families of hyperelliptic curves. So notice, again, in this first column, I have A, B. So notice every prime and every weight gives rise to a family of potentially bad examples. These bad examples would peter out by the 30th term, but they'd usually peter out quite early. These are the actual terms that are defective. So how do you use this table? If you have a weight like 12, you want to see P to the 11th, and you want to ask, is it ever the case that the third coefficient or the fourth coefficients or in these Lucas sequences correspond to the algebraic geometry? So let me explain how that works. So first of all, just some key lemmas about Lucas sequences. This is very elementary. If I gave you a Lucas sequence and D divides N, then the dth Lucas number will divide the nth one. I forgot if I mentioned this earlier, but this was implicit. This is why I was able to conclude earlier that D had to be prime. And I did allude to this earlier. If you let M sub L be the smallest index N for which L divides the nth Lucas number, well, this is an exercise to show that that index itself divides L times L squared minus 1. There are some counterexamples, but those counterexamples will correspond to situations which don't relate to our problem. The famous theory of new forms, together with this theory of Deligne, has these 4 facts. As I mentioned earlier, the Fourier coefficients of new forms are multiplicative. On prime powers, the coefficients satisfy this 2-term linear occurrence relation. And this 2-term linear occurrence relation can be rewritten in this way, so that the coefficients at prime powers are explicit terms in the Lucas sequence, where the roots that determine the Lucas sequence are the roots of Frobenius. And this is elementary calculation. And the last point is, of course, Deligne's famous theorem. All right, great. So what is the strategy for proving these theorems? So again, I'm only going to state the L case, the nth coefficient being a prime L in absolute value, but it's very easy to decorate this for any L to the M. So by Hecke multiplicativity, N must be a prime power. So we have a general theorem that says plus or minus 1 is never a Fourier coefficient after the first coefficient unless it arises from a U operator. Our mod 2 Galois representation condition and the Hecke recursion would then imply that this prime power is an even prime power. And then we note that this even prime power is the 2m plus first term in a Lucas sequence. Then we use the theory of primitive prime divisors to rule out the possibility that L is a coefficient that arises as a defective term. And then by relative divisibility, for a Fourier coefficient to actually equal L, it must be the first time L divides a coefficient, because by the theory of primitive prime divisors, the very second time L divides a coefficient, there's got to be another alien prime that divides it by the theory of primitive prime divisors. Is that clear? Right? If a Fourier coefficient ever equals a prime power L, it has to be the first time L ever divides a coefficient, because by ruling out the defective cases, the next time L divides it, there has to be a new prime that didn't divide any previous term. So because of that, this 2m plus 1 itself must be prime, where that prime has to divide L times L squared minus 1. So I know I feel like I've said this before, but I wanted to describe this strategy again now after I've told you a little bit about the primitive prime divisors. And so the rest of the work boils down to how to answer these questions, the question in red. These first 6 steps explain the location theorem that says that you can really greatly narrow the location of an odd coefficient. And so the rest of the work is how do you decide for each D whether or not there are any primes P for which A of P to the D minus 1 equals plus or minus L. And the nice thing about this is that this is actually a sublocus of an algebraic curve. So let me explain that. It's actually very easy. Suppose that A of P squared equals alpha. I leave it to you to just think about it. The famous Hecke relation relating A of P squared to A of P would tell you that the point P comma A of P is an integer point on this elliptic or hyperelliptic curve. So if alpha is plus or minus L, you just want to know, is there an integer point on this hyperelliptic curve whose x-coordinate is a prime? If that hyperelliptic curve actually has no integer points, you're already finished. That alpha is never a coefficient of A of P squared. How about A of P to the fourth? Well, we have a Hecke recurrence relation relating A of P to the fourth to A of P squared to the number 1. And if you combine them, you can check that this hyperelliptic curve with constant 4 alpha must have an integer point whose x-coordinate is the prime and whose y-coordinate is this ugly thing. But you can check if this alpha gives rise to a hyperelliptic curve with no integer points, well, you're done. A of P to the fourth is never alpha. Even if this has integer points, maybe you can rule out the possibility that an x-coordinate is ever a prime. If you were wondering why I knew that 37 could occur as a coefficient, but must occur at the coefficient 3 squared, it's because we found a hyperelliptic curve that actually had an integer point whose x-coordinate is 3. So if you're wondering why that works out, it's not an analytic number theory kind of estimate thing. This approach literally finds that the Fourier coefficients correspond to these algebraic points on these curves. And the conjecture is every such point on these curves corresponds to some modular form somewhere. More generally, if you want to study A of P to the 2m for m at least 3, we now just use the fact that the Euler factor is a quadratic polynomial in A of P and A of P squared. Combinatorially, that means let's write down as a power series in T 1 over 1 minus root y t plus xt squared. Then this fm of xy, when m is even, will be a homogeneous polynomial in x and m. So this m is this m, and now if we required this m to be now even, you can check that there's a closed formula for f2m of xy as a homogeneous polynomial. It actually cuts out the maximal real subfield of the 2m plus first cyclotomic extension. And so you can just check from this formalism that if af of p to the 2m ever equals alpha, well, it's because thanks to this, that this homogeneous polynomial evaluated at p to the 2k minus 1 and evaluated af of p squared would be the coefficient. Let me just show you what that means. So if y is AF of P squared, here this is 1 minus AF of P. And if we let x be P to the 2k minus 1, you see this is like the ordinary Euler factor when that you would get for the L function, which is why you can see that this is true. So I gave an explicit example earlier today saying that using this theory, we could prove that tau is never in these sets. And the reason is as follows. So for every prime, list the d's that divide L times L squared minus 1. There's a finite number of them. We have to rule out tau of P to the d minus 1 equaling plus or minus L. And what that means is we're either studying, and so now since the weight is 12, we're either studying one of 4 hyperelliptic curves, right? There's one for P squared and P to the 4th, and 2 choices of signs. So there's 4 hyperelliptic curves. So for every L in that range, we were able to rule out an x coordinate being that prime on any one of those hyperelliptic curves. Now, these d's that divide L times L squared minus 1 aren't only 3 and 5, right? It's one more than that. So it's not only 3 and 5. When it's bigger than that, well, we have these two-way equations, and we have the technology to solve and determine all the integer points on these equations. Please don't assume that it is easy. That's not easy. There's a lot of work that goes into it. So if you want to make our list longer, there's more geometry that has to come into play. And we're just very lucky that the range of primes I've described to you had the property that we were able to rule out those alleged points, thereby concluding that tau couldn't be those values either by doing by computing the Mordell-Weil group of the Jacobian and finding no integer points, or doing a Chabot-Coleman argument with p-adic integration, or doing some modified variant of the theory of linear forms and logarithms that have been applied to two-way equations. And thankfully, the whole combination of those ideas was enough to get this theorem. Great. And so to conclude, I didn't have time to explain this, but it wasn't very difficult. If you are interested in counting the number of prime divisors of Fourier coefficient, including multiplicity, generally, the most general result is better than just naive multiplicativity. Recall that little omega counts the number of distinct prime divisors of n. And this lower bound is sharp, and it holds for forms with my mod 2 representation condition. And the main results look like this. We've located where prime powers can be. And if you do some geometry, you can rule out many spaces for any fixed coefficients, like none of the primes up to 37 in absolute value are coefficients of new forms with weights -1 that are divisible by either 3 or 5. We have many examples like this, but this is just one. And in cases where we can't rule out, it's because they are there. The geometry of the curves dictates that they are there. And if you're interested in the aspect where the weights grow, our methods work so nicely that when the weights grow, and or at least where the powers grow, say you want to study L to the m, if L is fixed and m is growing, as a linear function in m, we know that weights growing at least linearly in m will be large enough to rule out L to the m as a coefficient in absolute value. So that's what I wanted to share with you. If you ever computed coefficients of modular forms and to say, not only are they multiplicative, but if you ever wondered, I wonder what coefficients, what numbers actually arise, the techniques that we're describing, I think, offer the first explicit theorems of this kind. And so today was about the situation where alpha is odd for these forms. And like I said, we already have some results when alpha is even but non-zero. And they're very much some of the same kinds of theorems, slightly modified in that setting. Great, thank you very much.
So thank you. So any questions? So if you have questions, please push your raise hand button.
Okay, so I will need help because I don't see the hands. So if you call on someone, can you have them just tell their question on microphone? I have to hear the question.
Any questions?
Oh, maybe no questions.
あ、金子さんが。
ん
金子さん。あ、金子さん、大丈夫。
はい、押しました。あ、金子さん、お願いします。
Masanobu, was that you?
Yeah, yeah.
あ、
Hey, how are you?
Hi.
Good to see you.
Very good.
Yeah.
Do you see me? No?
I don't see you.
パネリストにしましょうか。
ああ、せっかくだからにします。
I don't quite see you.
Ah,
It's
okay.
probably my fault.
No, no, no.
Okay.
I know I see you. I know.
It's great. Great talk. Great talk.
Well, thank you.
So low weights like 4 or 2 had
Yes.
some exceptions. Is it
Yes.
this is because of some Diophantine reason? Am I right? Or
Yes.
why?
Absolutely. Yeah. So there are some theorems. So for weight 4, there are theorems, right?
Mm.
Our paper will have that. Weights 2 and 3 are more problematic.
Mm.
Yeah.
And also, you showed us the Lehmann's example of prime value, huge
Yeah.
prime.
Yeah. Yeah.
Is that the minimal one, or you see the
Yeah.
example-wise? Yeah.
You mean in absolute value, or do you mean,
Yes,
you mean the first n for which tau of n is prime, or an absolute value is that the small one?
Absolute value of
I have no idea.
prime.
That's a very good
Okay.
question. So if you had an infinitely powerful computer, our theorems would allow you to check that. Yeah.
But in principle, the question absolute value of the questions becomes larger and larger when n.
Oh yeah, absolutely.
So
right. That's true.
is there any effective way to restrict up to some point that there's no possibility of finding such and such prime?
Right. So
There should be.
I mean, if you run our algorithm for every prime up to that, and you could actually solve the geometry problem in every case, that would be your answer.
Mm.
So in theory, that would work. If you want to have a heuristic, the Sato-Tate conjecture gives the distribution of the angles. And I think if you worked out, maybe assuming the Riemann hypothesis and Ramanujan-Peterson, maybe you could do some estimates that say that the prime coefficients that arise, there are this many up to x. You would never be able to show that that number is the best, but you might be able to guess something about not only the number of alpha up to x in absolute value that are hit, maybe you could do something.
Mm-hmm.
Yeah.
And my final question is, what is the expected ratio or density of prime coefficient of tau?
Oh, out of the primes, 0.
Out of the primes, yeah.
That's 0.
Yeah, density is 0, but some like log something over log.
Oh,
So this
this is a very
some
hard
heuristic. Mm-hmm.
Yeah, I have never thought about that problem, but I think I know how you would have to work in view. Ooh, very interesting idea. So you would probably, and I'm sure some of these people have thought about it. There are people like Mike Bennett and Cam Stewart and others who think very seriously about linear occurrence relations, and they probably have thought about the problem primes in linear occurrence relations. And whatever their heuristic is there must be what applies here.
I see.
Yeah. But there are there are definitely degenerate cases where there will be no primes in a linear occurrence relation. But whatever they must have thought about this seriously. And to answer your question, I would read that and I would probably just copy it.
Thank you very much. Thank you. Yeah, I was happy to see you.
Good. Yeah.
Thank you. Thank you.
Any other questions?
So if anyone has a particular number they want to have verified as not being a coefficient of a form for a good reason, just ask. We might be able to do it.
May I ask one question?
Sure.
Lehman's conjecture is the conjecture about the power of 24th, right?
Yes.
Is there analog for other powers?
Yes. Yeah, actually, there are many very precise conjectures. Professor Kaneko can also follow up on this. So if you want to study the powers of the Dedekind eta function, or the infinite product, 1 minus q to the n to the, say, s power, if s is bigger than 20, if s is, actually, I'd be very precise. There are very strong theorems that are known about the s power of the Euler product for s equals 1, 2, 3, 4, 6, 8, 10, 14, and 26. There's a very special list that Jacobi, Euler, and Serre found. Outside of that list, I think s equals 5 and 15 are the only ones for which any coefficients are known to vanish. Is that right, Masanobu? Isn't that right? I think the fifth power and maybe. So to answer your question, outside a finite set of positive integers s, outside a finite set of positive integer s, the conjecture is that the coefficients of the infinite product 1 minus q to the n to the s are never 0.
Okay, thank you very much.
Right. So here's the rule of thumb. Apart from, I think, the 5th power and the 15th power of the eta function, where there's some strange counterexamples, apart from those two, there's a closed formula in every other situation where 0 coefficients are known, either from like Katz-Peterson identity, or the theory of complex multiplication, or things like that.
Thank you.
Yeah, the McDonald identities give some others. Yeah.
Any other questions?
All right. Well, thank you for having me. I will talk, I guess, on Wednesday night. I have something different there. I'm going to talk about holomorphic quantum modular forms on Wednesday.
I see.
Yes.
So I have a question. So
okay.
you expect that the defectiveness also exists for mock modular form or something? Mock modular form?
So we would have to generalize what we mean by defective. So defective in today's talk was very precisely related to the Fourier coefficients on a fixed prime power. And so when we do a mock modular form, apart from those that come from Eisenstein type, when we study mock modular forms, we don't have this two-term linear occurrence relation on the Fourier coefficients. You can have something like that p-adically, but it's a little bit funny. But if we were to extend what we mean by, if we were to extend what we meant by defectiveness, that is a very interesting question. Is it literally true that if you were to walk through an arbitrary infinite sequence of coefficients of a mock modular form, would you find from some point on that the next coefficient is always divisible by something you knew before? I mean, you did not know before? No, that's false. I think I can find you a counterexample to that.
I see.
But probably not far from true. So if you're interested in that, I think Professor Kaneko also can talk a little bit about this. There is this very famous work of Gross and Zagier on the factorization of norms of singular moduli. And if you take norms of differences, if you take the difference where one of those differences is 0, it's really just the factorization of singular values. But if you factorize, and these turn out to be coefficients of a weight 3/2 modular form that Don Zagier studied. And it turns out that the prime divisors of them are very, very carefully constrained by some discriminant conditions. And it turns out that there are mock modular forms that enjoy the same kinds of singular moduli formula. They are values of other kinds of functions at singular moduli. And I think that kind of factorization property maybe isn't proven in many cases, maybe not any cases, but might exist. So I suspect that that's the case. So to answer your question, it's a great question, but you would have to reformulate it, and there will probably be, you would probably have to allow for some flexibility.
I see.
Yeah.
Okay, thank you.
Yeah. Strictly speaking, I could imagine there might be a few rare counterexamples. Yeah.
So any other questions? Okay, thank you again.
Okay. All right. Thank you, everyone.
Thank you very
My
much.
bedtime. All right. See you later. Have a